guys. So this is a video just to show you how to use your gel image to make a standard curve and how to use that standard curve to determine the sizes of your unknown fragments. So let's say you're working through your gel analysis, you've already taken a look at your gel, and you've made estimates of how big these unknown bands are approximately. So from here we need to make a standard curve. In order to make a standard curve, you need to measure the distance from the well to the bands in your ladder. So you're trying to figure out how far did, say, this, like, we know that this band is a 10 kilobase piece of DNA. How far did it move from the well? Usually when you're doing a standard curve, you would print out this gel photo and you would take a ruler and you would actually measure. So you can do that if you have access to a printer and you have a ruler lying somewhere around your house. If you don't have a printer, you can also take a ruler and just hold it up to your screen and measure from the well, and you want to measure from the bottom of the well to the bottom of the band. So you could do that. If you don't have a printer or a ruler, then what I would suggest doing is opening up a PowerPoint presentation and just kind of plopping your gel photo into it and getting an image of a ruler. So you could just Google this, or I posted this image on Canvas so you can use it because I think it's a pretty nice, easy to use image. And it doesn't really matter that these centimeters, that this is not to scale, because what you're interested in is the relative distance that each of these bands moved. You know that smaller bands should move more quickly and so further than larger bands, but you want to know how much so that you can compare how far these moved to how far these moved. So you really don't have to worry about the fact that this is an image on your screen that doesn't necessarily represent a real world centimeter. So you can just take your ruler image and line it up like you would a ruler at the bottom of the well, and then start measuring the distance from the well to the band. So here, from this to this band right there, that looks like it is about 1.1, 2, 3, 4. I'm going to call that 1.4 centimeters. And I would suggest getting an Excel file for yourself and just kind of entering in. So you can see here I've set it up so that I'm making my standard curve and I am now recording the mobilities of each fragment. So we'll go back over here and now measure down to this band. So that looks like it's, I'm going to call that 1.6 centimeters. And that one is 1.9. And so you just want to do this for every band in your ladder. Alright, so as you can see, I've now filled out all my mobilities into my Excel table. And when you do this, you'll have a lot more numbers here than I do, because as you've probably noticed, my gel image is not the same as yours. I kind of made this sample gel image with a different ladder and different enzymes than yours. So if you're getting different numbers than I am, that's why. But as you'll see, I filled out all of the mobilities of all these fragments in the ladder, and I also filled in the sizes of the DNA fragments in each of these bands. So that's just what's over here, kind of to the left of the gel image. So for example, this band is made of 10 kilobase DNA, so I put 10 kilobases in the table next to it. This band is 8 kilobase DNA, and so on. One thing I want to point out that could be confusing is that down here, this band is labeled 2 times 0.5. The DNA in that band is 0.5 kilobases. It's not 1 kilobase or anything. The 2 times is just to show that there's twice as much DNA in that band to make it a little brighter. But the size, so what you want to put in your table, is 0.5. The other thing that I want to kind of draw attention to is you'll notice that the relationship between how far this DNA, these DNA standards have moved, and their size is not linear. Like for example, if you look at this 10 kilobase band and this 8 kilobase band, there's 2 kilobases, so 2,000 base pairs, difference between the sizes of the DNA in these bands, but they're really not that far apart. Whereas if you look down at the bottom of the gel, this 1 kilobase band and this 0.5 kilobase band, so there's only half a kilobase or 500 base pairs difference between those two, but they are a lot further apart. And so because of that non-linear relationship, you can't just make a standard curve of like using a linear graph. We have to use a logarithmic graph. One way you could do this is to use a log scale on your axis, but that's actually kind of hard to do on Excel. So what's going to be easier for us to do is just transform our data. So you have the size of your DNA standards, and now you want to take the log 10 of each of those sizes. So on Excel, you just type in log, click there, and now it's taken the log 10 of your DNA size. And so you just want to make sure to do this for all of your DNA. And now we can plot this data as our standard curve. So for your standard curve, you want to plot this mobility column on the x-axis and this log 10 of DNA size on the y-axis. So what I think is easiest to do is to just select this column, copy it, and put it down here. Select this column, copy it, and also put it down here. Because the values in this column are the result of an equation, if you paste it directly down here, you won't get the right numbers. So make sure that you go to paste special and just paste the values. And now you can see the numbers are the same. And now you can highlight both of these columns, and you want to insert a scatter plot. So we go to scatter, and there is your standard curve. So you may be a little bewildered by the fact that it crosses the x-axis and that you have some negative values, but don't worry about that. The reason for that is because you are going to numbers less than 1. And so taking the log of something less than 1 gives you a negative value. If you really hate the fact that you're getting negative values, something you could do is instead of having this DNA size in kilobases, you could have it in base pairs instead. So you could write this out as 10,000, 8,000, 6,000, all the way down to 500, and then all of your log values will be positive. If that sounds confusing, just leave it this way, because it will, both ways will get you what you want. So we're just going to stick with this graph. You want to kind of have a linear line. If you don't have something that looks vaguely linear, double check your numbers because something might have gone wrong. And of course, for when you're going to submit your assignment, you want to make this graph look kind of nice, like you do not want this title here. You want to add some axis labels, but you know how to do that, so I'm not going to show you that. What you want to do now is draw a line through this. So you can right click on your data points and click add trend line. And there's our line. And then down here in this format trend line pane that's open, you can display the equation of the line on your chart. If you want to, you can also display the r-squared value. And the closer this is to 1, the better the fit the line is to your data. So this is like not perfect, but pretty close. Good enough for us. And so this is the relationship between the mobility and the fragment sizes. So what you can do now is measure the mobilities of your unknown fragments and plug them into this equation. So let's turn our attention back to these lanes where we have our restriction digests. So we want to measure the mobilities of these bands just like we did with the ladder. So again, we're going to take our ruler and we're going to measure from the well to the band. And this looks like it is 3.8 centimeters. And this one looks like it is 4.5. So these are the two fragments we have in lane 1, whatever restriction digest this is. And so because you're going to eventually measure all of these bands, you want to make sure that you're keeping track of which mobilities go to which lane or which digest, so that way you can match the fragment sizes you're eventually going to get to the right digest. So I'm just going to record which lane these are in. So these were both in lane 1. And now we can move our ruler over and measure the bands in lane 2. So that is 2.2 centimeters. And this one is 4.567, 4.8. Lane 2. And I'm just going to do these two. Of course, for yours, you would also do your double digest. But since I'm just showing you, I'm just going to take these numbers and now plug them into the equation we got from our standard curve, because on the x-axis is the mobility. So these are x values. And now we want to find the log size of the DNA, which is going to be our y value. So if we look at, I'm going to move this chart up a little bit just so that I can type the equation in here. So we're going to be plugging in whatever's in this column for x. So the equation is negative 0.2498 times x. So times this plus 1.2779. Okay, very good. And you're going to plug all these values into that equation. So now we have the log 10 of our sizes, and we need to take the anti-log to figure out the actual size in kilobases. So if anyone needs a refresher from algebra, the anti-log of a log 10 equation is just 10 to the power of whatever this is. So, oops, I forgot to put in the equal sign. So equals 10 to the power of whatever's in this cell. Oh dear. I'm gonna do that again. There we go. Cool. So the very last thing that you want to do once you have all of your sizes for your digest is you want to see, do these numbers make any sort of sense? So that was why it was important in the first step of your gel analysis for you to just look at the gel and make rough estimates of what size you thought these bands were, just visually compared to the ladder. Because now what we can do is we can see, like, all right, so for this first band in lane 1, it looks like we got 2.13 kilobases, and this band looks like it's a little bit larger than 2 kilobases because it's a little bit closer to this well. So that makes sense. And that is kind of like a confirmation that we did our standard curve right. Of course, once you are, reassured that you did your standard curve right and that your sizes are accurate, you can then compare the sizes that you got in your digest and based on your standard curve with the sizes that you expected for each of the plasmids when you did your snap gene exercise. And that will help you determine whether you got PATC or P-glow in your sample, and also kind of how well these sizes match up with what you expected will allow you to kind of draw some conclusions or talk about in your discussion whether you think these enzymes worked well for differentiating these plasmids or not. So I hope this was helpful. Of course, if you get lost, you can always send an email, post in the discussion to ask questions.